find the coefficient of friction, that's not one of the two things that you can find using Newton's laws. I want to remind you about that. All that Newton's laws can tell you is the size of an individual force or the size of the acceleration. That's what Newton's laws can tell you. But we have a definition out there from just yesterday that tells us about a relationship between the frictional force and the normal force. So if I want mu, it appears that the best way to do so would be to find an expression for the frictional force and an expression for the normal force. If I can find those two expressions, I should be able to figure out mu. And since Newton's laws can tell me the size of an individual force, seems to be my job is to use Newton's laws to find the size of the frictional force and the normal force. Now, if you didn't reason that out, that's okay. You should still be able to start the problem. There are clear clues as to why this is a Newton's law problem, as opposed to an energy problem or a momentum problem or a harmonic motion problem. So when we are attempting to discern on the actual AP exam what is the best thing to bring to bear here, the biggest thing is individual forces were given in the problem. That steers you to only two possible things that you could probably be doing: Newton's laws or work. So when we start looking at having to decide why I would use Newton's laws to solve this, well, Newton's laws can solve any question. It's just how hard you want to work on it. So you try other things first if you can. But this one, you don't have many options. Walking around the room, I did notice that there are a few of you who are just kind of refusing to do things the way I asked, but some of you are doing it expertly. I'm glad to see that. You don't get any choices here, do you? Once you've decided whether this is a first law problem or a second law problem, what you do next isn't up to you. It's up to a set of rules. And I've had a couple of conversations with students in the last 3 or 4 days that have been a little bit disturbing. You don't make choices here. The choices are made for you after you decide whether it's a first law or second law problem. And this is a first law problem. It's clear from the beginning. Moving at a constant 2 meters per second. Now you are told what to do. Is gravity acting on the box? Yes, it's acting on every box. That is a downward arrow. Size of that arrow, 200 newtons. You put weight there if you want, mg if you want, or 200. It's a 20 kilogram box. Is the box in contact with any surface? Yes, it is touching the ground. You don't get a choice here. There's only one way to draw this. The ground can't pull, it can only push, which means away from the ground. Yes, I drew it less than 200 newtons. Why? Because there's another force there, a pulling force, that is also pulling up on the box. I'm going to get a choice on this one. Something is pulling. I'm given everything about this force. I don't even have to think about it too much. Meaning they told me about this force. I don't even have to name it if I don't want to. Tension, fine. 75 newtons, fine. You don't get a choice. Now, I'm going down my list. Is there any reason to believe that there is a resistive force acting on the problem? Yeah, because otherwise this doesn't look balanced to me. There needs to be something that pulls to the left. I don't know what direction to the left, except I do. If I think friction, which is a force that prevents one surface from sliding past another, if I believe it's working, the only possible way friction can be acting is one of those two, either left or right. You have an A-B choice here, and I know I hate leaving choices up to you, but is friction going to help the box move or try and prevent it from moving? So I don't know that it's really a choice so much. Now, there will be times when friction causes something to move. Certainly. Happens to you all the time. But this is not one of those cases. And unless you're told there is no air resistance, We have gone down the list. We have identified all the forces that are acting in the problem. Does our system look as though it's balanced? Yeah, there's some problems with this diagram. Friction seems to be larger than the normal force. Would I mark you off on it? Maybe. Seems to me probably the normal force is greater. Or maybe I've drawn this too long. I need to identify a coordinate system. I have two choices. Either align it with the direction of the acceleration or align it with the most number of forces possible. Or give myself way more work than I want to do. So it's not accelerating. But I've got three forces that are perpendicular to each other. It seems quite reasonable to align this with those two forces. I'm sorry, those three forces. That makes the most sense. Unfortunately, that does not resolve all the forces. The phrase resolve forces is what I use to say break forces up into their components. That's what I mean when I say resolve forces. From this point forward, I'll probably only say resolve forces. So you have one force that you have to resolve, and that's that 75 newtons of tension. It's got a component in this direction and a component in that direction. This is the opposite side, so it's 75 sine 30. This is the adjacent side, 75 cosine 30. And yeah, I am done doing trig. If you're not, because your trig experience has been crappy, no, it's on you. Fix it. Get help. Or write sine and cosine down every single time. But learn. The adjacent side is going to scale the vector by the percentage given by cosine. And the opposite side is going to scale the vector by the percentage given by sine. Sine and cosine are giving you projections of the vector along the axes. Really, we're done now. We've done all the work. Net force in the x direction, net force in the y direction. And the sheer number of times I've done this, it still bothers me when people don't recognize that the only thing that can be in the x direction are forces that point left or right. So 75 cosine 30 minus friction equals 0. I know I didn't mark a positive or negative on my coordinate system. I'm hoping you understand things that point left have to be given a different sign than things that point right. And you have to be cognizant and thinking about that without having to be prompted. And things that point up are probably going to have a different sign than things that point down. So normal plus 75 sine 30 minus 200. Seems to me you can find friction in a normal force now. And with that, you can find mu. Level of difficulty here, actually not very high. I'm going to put this at a solid, 5 out of 10. There's a lot of things that have to be done right, but a lot of it is repetitive in nature. All right, questions about that? Okay. I want to talk today about friction quite a bit, but I want to point out I have given you a homework assignment. I want to finish our discussion on the types of friction. I like this problem because it offers me an interesting situation. So consider this situation.
At this time, you can release any student who has an NHS club card.
Interact. You've done a lab now on kinetic friction. This problem is a kinetic friction problem. It really doesn't have a whole lot of interesting things to me. But to ensure that you guys are truly on the ball about this, let's see if we can flip the script a little bit on you. The inclined plane problem tends to be where people start tripping up when it comes to using the ideas of kinetic friction. So if I have an inclined plane in a box, and the box has a mass of m, and the inclined plane angle theta not 100 in theta, just theta. And there's a coefficient of kinetic friction of mu k. Can you give me an expression for the acceleration of the box? Let's assume the box has been given a little nudge, not a constant force, just a poke to get it started, and it's accelerating. Now, I don't know if you guys are capable of doing this or not, but I'm going to tell you again, I'm looking for A equals it's not universal, but 5 or 6 folks. Is this a second law problem or a first law problem?
Second.
All right. So net force equals MA. Now, regardless, I'm being asked about an acceleration. That's something that net force can do. So let's see if we can get net force to do that for us. I'm going to start, at the free body diagram. And in this case, you don't get any choices. You just draw the things as they happen. So I'm starting with gravity. It's a force that has to be downwards. So anytime I see somebody with a force drawn incorrectly, I know it's because either they're not thinking it through or they're not really paying attention. So I'm going to go with not thinking it through. But this is mg. It's in contact with the ramp. So if I'm going to draw a force from the ramp, it's got to be perpendicular to the ramp. I don't get a choice about this. So it's not up. It's perpendicular to the ramp, and it has to be away from the ramp. It can't be into the ramp. The ramp can't pull the object down. You can only push it away. We know there's friction. We don't actually necessarily know the direction the box is moving, but it's implied that it was given a tap. So I think the box has been tapped so that it's moving down the ramp. So that suggests to me that if we're looking for the direction of the frictional force, and I know I have only 2 options, down the ramp or up the ramp, what direction do I believe friction is acting? Well, I believe it's acting up the ramp to prevent the box from going down the ramp. But it's a choice you have to make. If the box had an initial velocity up the ramp, then friction would be down the ramp. And don't not think that I can't do that on our next practice. So, you need a coordinate system. Someone's going to help you analyze all of this. And we've talked about this enough where I don't want to have to go through why we're going to use a coordinate system lined up with the horizontal axis. But it comes down to priority number 1. Priority number 1 is to place the coordinate system in the direction of the acceleration. The only way the box can accelerate is up or down the ramp. It's not going to accelerate up. It can't. It's confined to motion that's up or down the ramp. Now, you also have to decide on what direction you're going to call positive. Make life easy on yourself. Make the direction of motion positive. You will be happier, I promise. That's down the ramp, by the way. That makes up the ramp negative. If you don't obey that, you still get the right answer, but then you have to be careful about how you deal with acceleration. Because acceleration has to obey the same positive and negative as your net force. So I'm just telling you, if you want to make your life easier, always make the direction of motion the positive direction. But you do you. You guys don't listen to me, and then, you're wondering why your grade's in the toilet. I already explained this. Theta goes there. Yep.
Sorry, I'm just curious. On our test, do you want us to have the axis turned, or can we immediately have it faced right up?
I saw enough of you that are facing it, so that your axes are back to being horizontal and vertical. That's up to you.
Okay.
the AP graders tend to not care about your work, but the free body diagram should match the direction of the weight. So don't do this to your free body diagram if you're having one that you're having graded.
Okay.
Does that make sense? Okay. I see only one force has to be broken up into components, and that is the weight. Had a few of you do this incorrectly, more in AP1 than in this class. But remember, the weight is the hypotenuse. You're finding the components. Components have to be perpendicular to each other. There's a few of you who try to draw this line. That's not a good idea. Don't do that. Now, this is the amount that is in the negative y direction, and this is the amount down the ramp, because cosine goes with the adjacent side and sine goes with the opposite side. So there we go. We don't have a solution yet, but we are at the last stages of what Newton's laws can do for you. And that last stage is to say net force in the x direction equals ma. We purposely chose the direction of our axis so it would get the acceleration. Net force in the y direction equals 0. We purposely chose to orient our axes to make one of these 0. That's why. You don't have to do it this way, but then acceleration would be in both. And you don't know how much of the acceleration is in both. That's a bad way to do it. However, in the x direction, there are only two forces. One of them is down the ramp. I'm making that one positive, and one of them is up the ramp. I'm making that one negative, and I'm setting them equal to ma. That's it. That's all I can get from the net force in the x direction. Net force in the y direction, I can get normal force equals mg cosine theta. I know, I should write n minus mg cosine theta equals 0, but come on. They're balanced. There's only two forces. They have to be equal to each other. So that's the end. That's all that net force can do. It's your job to see if you can do more. I have a solution. I have acceleration. You could stop there and just divide by m. Except, I never worked this mu k into it. I probably was given that for a reason. And it's at this moment where we're adding to what you know. Some of you have never done this before. Which means, listen closely, I expected that everybody in the room, regardless of past experience, should be able to get to where we are right now. This is no different than what we've been doing for the last week and a half. What we do next is new for people who have not done physics before. This is the line. So I am expecting you could get here. If you couldn't get here, you need to pick up the pace a little bit, and I will help you if you need it. Come to tutoring. At this moment, you have to understand there are more tools that we have. They're not net force tools. They're just more things that you need to know now. So let's talk about those things that you need to know now. We are told that there is a relationship between friction and the normal force. I am kind of expecting now that you can use this knowledge to make substitutions. I'm just going to say this out loud. This equation is how you bring the x direction and the y direction together. That's what it's for, at least as a problem-solving component. So that's what I need you to do. I need you to make the substitution. This will allow you to have something from the y direction that can be substituted into the x direction. So that's what we're going to do. We have this expression for the friction. So mg sine theta from here minus mu k mg cosine theta equals ma. Substitution. And there's one of those in every one of those. And mass can't be 0, so I'm not dividing by 0. So, bye-bye. So listen closely to the following question before they interrupt us. Is the block speeding up or slowing down? Interesting. Interesting. I never said. Yes, sir?
Does it depend on what data it is?
I think it depends on more than just what theta is. It definitely doesn't depend on what G is.
Yeah.
Right? G is in both terms. So it doesn't depend on what G is. But yeah, I think theta plays a role in it. Sure. The bigger theta gets, the bigger this side gets, and the smaller this side gets. It also depends on mu, right? Mu gets bigger, the right side gets bigger, and the left side doesn't. You see, anytime, and this is a problem-solving like note, something that should be like highlighted in your notes, and maybe even put a sticky note on the outside so you can come, because this is like an important thing. You see, in the AP exam, you're going to be asked to make decisions. And sometimes you're going to be asked to look for analysis. Negative signs in equations are important because they represent inflection. They represent the chance for there to be a positive answer, a zero answer, and a negative answer. If this was a plus sign, I couldn't ask that. I would have no question. If it was a plus sign, it was going to be positive no matter what happened. But a minus sign right here, well, that's huge. Whenever you're subtracting two things, that's huge, especially if it's in the denominator. If you're subtracting two things and it's in the denominator, you have a chance for an infinite answer. Be careful. Subtraction in an expression is valuable because it means there's a possibility of two or more results. I have no idea if this thing is slowing down or speeding up. It will depend. In fact, it's this kind of equation that lets me know exactly how to set it up so it will speed up or will slow down. Right? If I know what mu is, and I want to make sure boxes don't accelerate down ramps, I choose an angle to make sure it never happens. If you're trying to engineer something, these are the kinds of things you look for in engineering. If I know I have a fixed angle and I want to make sure stuff doesn't accelerate down the ramp and slows down so you don't break stuff, well, then I probably have to choose the right angle for that too, to ensure it always stays positive or always stays negative. And if I don't want it to accelerate at all, then make it zero. Right? I can do that too. So whenever you have a negative sign in an expression, you should stop, take notice. It's important. They don't just show up arbitrarily. This is the level of your test, this level of work. And I don't mean getting this answer. I mean getting this answer and answering the question, does the object speed up or slow down, and be able to explain why this expression can tell you the conditions when it would speed up or slow down. Does everybody understand? That's what I will expect you to do on your next test. Want to try another one?